Hi all, this is the third video on functional analysis. Here we discuss something more about quotient spaces. The outline goes like this. First we will discuss examples of quotient spaces, then a lemma about codimension of finite dimensional quotient spaces, then some geometrical discussion on coset addition. So coming to the examples of quotient spaces, in first example, we have the vector space E equal to the set of all infinite tuples, that is f raised to infinity. And the subspace we are taking here, E1 is equal to collection of all 0, x1, 0, x2, x3, etc. infinite tuples with first coordinate 0. Here we can easily note that any two elements of E determine same elements of the quotient space if and only if they have the same first coordinate. Hence, an element of the quotient space is just determined by the value of that first coordinate x1. This gives an identification of the quotient space with the field of scalars f itself. Here, we can note that the vector space and the subspace are infinite dimensional, but the quotient space E by E1 is finite dimensional. That means here it is one dimensional. Now in example 2, we will have some exact example of what we have discussed in example 1. Here I am taking explicitly E is equal to R2, the Euclidean plane, and E1 is actually the set of all ordered pairs x1 0 such that x1 element of R, what is it? It is a real line, horizontal real line. Then the quotient space is the collection of all horizontal lines in Euclidean space, that is with dimension 1. Here the subspace is the horizontal x-axis, and each coset is a horizontal line parallel to this subspace. So the quotient space will be the collection of all horizontal lines in the Euclidean plane. Next example, here we are taking the vector space to be the space of continuous functions on R, and P be the subspace containing all the polynomials. So I am taking now a specific polynomial f element of C of R, and the coset determined by f is f plus p, that is the collection of all small f plus p where p is a polynomial. So if we have two cosets to be equal, that is f plus p and g plus p are equal if and only if f minus g is a polynomial. So what is the coset f plus p? It is the equivalent class obtained by identifying functions which differ only by a polynomial. So the quotient space will be the collection of all such cosets. Now we come to the codimension of finite dimensional vector spaces. We cannot find the dimension of infinite dimensional vector spaces, so we are constraining it to finite dimensional vector spaces. Here in this lemma, the lemma says that we discuss about the codimension, and the lemma states that if the dimension of the quotient space is n, if and only if there exist x1, x2, etc. xn linearly independent vectors relative to E1, such that for every x element of E, there exists a unique set of elements a1, a2, etc. an, and a unique vector from E1, that is y element of E1, such that x is equal to summation I is equal to 1 to n a xi plus y. Moreover, the cosets coset x1, coset x2, etc. coset xn of such vectors forms a basis for the quotient space. Now we go to the proof. In the proof we have if and only if condition. So first we will suppose that the dimension of the quotient space is n. Then we will prove the linearly independent properties or conditions given. So if the dimension of the quotient space is n, we can find n linearly independent cosets. That is, here I am taking coset x1, coset x2, etc. coset xn be a basis of E by E1. Then the vectors xi for I is equal to 1 to n are linearly independent relative to E1. So we have summation I equal to 1 to n ai coset xi element of E1. Something element of E1 is the subspace. So something element of E1 means this coset is the 0 coset. That means summation I is equal to 1 to n ai coset xi is equal to the 0 coset. That implied and implied by summation I is equal to 1 to n coset ai xi equal to 0. This we get by some algebraic manipulations. That means summation ai xi equal to 0. Then since xi's are all linearly independent, it is obvious that each ai equal to 0 for every I is equal to 1 to n. Thus we proved linear independence. Now we have to prove the spanning property. For that I am taking some coset x and thus x element of E, the vector space. So coset x is equal to summation I is equal to 1 to n ai into coset xi. So again, since it is element of E1, I can take it is summation I is equal to 1 to n cosat ai xi. Since x element of E, we have x is equal to summation I is equal to 1 to n ai xi plus the representative element y from E1. Now we have to prove that the uniqueness of the representative element, that is y. In order to prove the uniqueness, we are taking some z instead of y. So x is equal to summation I is equal to 1 to n bi xi plus z, where z element of E1. Now we can equate both two equations, that is from the previous slide, this equation, and this is x is equal to something, here also x is equal to something. So equating this, we will get summation I is equal to 1 to n ai minus bi xi is z minus y. Z and y are elements of E1. E1 is a subspace, therefore z minus y will be also element of E1. Then we should have this ai minus bi is equal to 0. That means each ai will be equal to bi. Thus we got y is equal to z. So the uniqueness is proved. Now we move on to the converse part. So for the converse part, we suppose that x is equal to the linear combination summation I is equal to 1 to n ai xi plus y, where y element of E1. And we are taking x1, x2, etc. xn are linearly independent vectors relative to E1. That implies cosat xi for I is equal to 1 to n are linearly independent relative to E1. That means we are taking the algebraic manipulations here. So summation I is equal to 1 to n ai cosat xi equal to E1, implied and implied by summation I is equal to 1 to n cosat ai xi equal to the 0 cosat. That means the element summation I is equal to 1 to n ai xi is in E1. That means each ai is equal to 0. Then that is the linear independence condition. Now we move on to spanning condition. Let x be any arbitrary coset. Since x minus summation I is equal to 1 to n ai xi element of E1, we can see that cosat x is equal to cosat summation I is equal to 1 to n ai xi. That is summation I is equal to 1 to n ai into cosat xi. Therefore, cosat xi, the collection of all such cosets, cosat xi is equal to 1 to n form a basis of E by E1. Now we have, before closing this, we have some algebraic geometric discussion on the coset addition and scalar multiplication of cosets. So we are taking a quotient space. I just want to show you it is in geometrically that how coset addition is happening. So here we are taking the vector space to be R2, the Euclidean plane, and the subspace here is R, the horizontal line. Here I am getting a coset E1, coset of E1, then this is also a coset, then we have many cosets. Okay, so here the quotient space E by E1 is the collection of all lines parallel to the horizontal line. Now we are coming to the concept of addition of cosets. So here I have the subspace E1, the black line horizontal. Now I have some cosets and I am having the green line here as coset x. The representative element is x. It is the black dot, and x is the ordered pair mn. So I am taking the position vector of x. Then I am taking another coset. Now I am coloring it with orange color, and I am taking a representative element y. Then the position vector, the y is ordered pair vw, and position vector of y will come like this. Now what I am going to do is I am going to add these cosets. So what I am going to do is I am adding the representative elements x plus y using the parallelogram law. So it comes like this. So we got a new point PQ, and this point is x plus y. So making this x plus y as the representative element, I have the new coset x plus y, that is in red dots here. Okay, so that is what happening in the addition of cosets. Now we will move on to what is happening in scalar multiplication of cosets. So here this black line is the subspace. Now I have my coset here, orange color. Then the point x is the representative point. I am taking x as mn. Now I have a non-zero scalar k. So I am multiplying this position vector with k. I am getting another position vector. So the tip is at PQ. That means the coset kx has the representative element kx. So again this red dotted line is the new coset, that is coset kx. So this is what happening in